Okay, for those of you still suffering from insomnia, I'm back. Anyway, we're going to discuss the DC characteristics, and it's basically the DC transfer characteristic of the inverter that we're interested in, although many gates tend to look the same. It's a transfer function because it's a transfer function of V out versus Vn. So this is Vn on the x-axis, V out on the y-axis, and superimposed here just happens to be the current that you would have flowing through those devices at a particular value of let's say Vn. Okay, we're going to be interested in these 5 regions of operation. The first one is region A, and in region A that basically corresponds to the case with the NMOS device and cutoff and the PMOS in the linear region. And the output voltages would be as follows. The input and output voltages Vin is less than Vtn because the NMOS device is off, and Vout is going to be pinned to VDD. Vout is found by equating the IDS for both the NMOS and the PMOS equation in their respective modes of operation, so it's pretty easy to calculate in that particular case. Region B, it's going to get slightly more complicated because VDD is now a function of Vn. PMOS remains in the linear region, and the NMOS device would go from cutoff into the saturation region. And this could be modeled as a current source when we know it's in the saturation region, and the PMOS device would be modeled as a resistor for using that simple linear equation for the device characteristics. In that case, again, we just equate the current for the N-type device to be equal and opposite to the current for the P-type device, and then we just get the equation down below here, or something that resembles it in any event. So VTP is the threshold voltage for the PMOS device, VTN was the threshold voltage for the NMOS device, and beta N, beta P were the transistor gains for those devices. So, in class assignment 3.5, why is this equation clearly incorrect? A hint to figuring that out is do some dimensional analysis on it, and you'll see that it obviously can't be correct, but I guess this part isn't in class, but I want you to derive the correct equation. Region C is a little bit trickier, and we're really just going to end up making an approximation here. We're going to let Vn equal to VDD by 2, and we'll sort of make an argument that Vout has to sit in this range here of Vin minus Vtn less than Vout, and it's less than or equal to Vn minus Vtp. So this would be, let's say, Vn minus a volt, Vn plus a volt when Vn was equal to VDD by 2. So both of those devices are in saturation. They're basically flat lines, and since we were looking for the intersection of 2 lines on a graph, clearly no analytic solution would exist for those simple little equations we were looking at. But you could do that if you wanted to. You'd end up with something like that, and all you'd end up seeing is that at least the equations are consistent. Region D is the region we're going to look at here, and that's going to be again synonymous to that region B case we looked at, where PMOS now stays in saturation. The NMOS device goes into its linear region, and in this case we model the NMOS as a resistor. We model the PMOS as a current source. We equate the current source for the N-type device being equal and opposite to that of the P-type device. So in this particular case, we have Vin is going to be greater than VDD by 2, but less than VDD minus the absolute value of the threshold voltage for the P-type device. So this might be, for example, 5 plus, let's say, minus 1. So it would be 5 by 2, so between 2.5 volts and 4 volts in that particular case. And this equation probably looks approximately right, although can't say that I derived it, I just cut and paste it from somewhere. And the last regime we'll look at is region E out here, where Vn is going to be large and Vout is going to be equal to 0. So here we're saying that Vn is greater than VDD plus VTP. So again, that's a negative number. So we're just saying in a 5-volt technology, for example, that Vn would be greater than, say, 4 volts if the threshold voltage were 1 volt. In that case, Vout is equal to 0. In the same kind of scenario, we equate the current through those 2 devices. Look at some example values. When this would be the case, we could say, well, Vn might be 4.5 volts. And then Vout would be 0, as we'd expect with an inverter characteristic. So with respect to, let's say, the drive strength of these devices, beta N over beta P ratio, if the N-type transistor is considerably stronger than the P-type transistor, we'd expect it to pull it down sooner than when the case is when the N-type device is weaker than the P-type device. We expect it to pull it down after the VDD by 2 point. One thing you can calculate on these things, which we'll want to do, is this region here where the slope is equal to -1 or slope is equal to -1 here. And these are going to be used for calculations for noise margins. And the way you'd go about calculating this point is you have the equation for that V out versus V in that region, and you differentiate it and set the slope to -1 and find out what your solution is. So with respect to the different beta N, beta P ratios, remember that was the drive strength of the transistors. These are the values, the mu Cox W over L, and it would be, let's say, mu N or mu P depending on the device. The only thing you as designer may have some control over is the W. And keep in mind that the mobilities are more mobile than holes. You certainly don't have any control over the oxide thickness, and really have limited control over the channel length, because you tend to make that as small as you possibly can, and to get more drive you make the device wider. Just a couple comments on how beta varies as a function of temperature. Just point out a couple places here where a drop in temperature raises the absolute value of the threshold voltages, and as you might expect, then the device tends to be less dissipative in terms of energy or power. It doesn't heat up as much. An interesting thing you can do once you have the transfer characteristic, you can look at noise margins, and this is the scenario we're looking at. Let's say inverter 1 driving inverter 2, and what we really want to be able to have is we want to have a big swing on the input voltage and have a small swing on the output voltage. So since there's 2 inverters in a row, this is sort of basically a buffer. But if we were looking at this point and this point, we'd have a big swing on the input, let's say for a high, and a little swing on the output for a low. And conversely, we could have a big swing on the input voltage, and the output voltage would be just a small swing associated with it. So often what we'll do is we'll associate this VOH and the VOL to being equal to VSS or VDD, and really just interested in this VIH level and this VIL level, and that's where I pointed out before where the slopes on these transfer characteristics were equal to -1. So with having that, when we go back to the picture, we have a useful tool for being able to calculate some of the noise margins associated with these devices, and this is the kind of specification you'd be able to read associated with that particular technology. And at that point, we'll take a quick break.